Performance optimization can be a complex art, as it involves understanding and manipulating many complex factors. These factors range from physical components, such as the temperature of a machine in a data center, to architectural factors, such as the choice of synchronous versus asynchronous communication patterns, or implementing back pressure for load management. And while I try to cover a lot of ground, from high to low level concepts, this course does not have an exhaustive list of everything you can do to make your application performant. Some of the topics not covered are micro-benchmarking, statistical measurements, database query tuning, and concurrency basics, for example. There are many great courses on Pluralsight that cover many of these topics, and I encourage you to spend some time in these courses to get the insight they contain. Some of the things you'll learn in this course are how to understand the performance characteristics of your applications. Here, you'll be introduced to the industry standard measures of application performance, learn how to do application monitoring and performance testing in Java, and learn what tools are good to have in your performance testing tool belt. Next, you'll be introduced to Java profilers, understand the different types of profilers, and walk through how to use the Java Flight Recorder to examine different aspects of an application's performance and to troubleshoot performance issues. Then you'll learn how to tune the parts of the JVM that are critical to performance, namely the garbage collector and the JIT compiler. Garbage collection is a popular topic when it comes to performance tuning in Java, so we'll look into how to monitor garbage collection, how to choose a GC algorithm, how to tune the different algorithms, and how to find memory leaks. Next, you'll explore topics in search and data structures, such as choosing the appropriate Java collections classes and search algorithms, understanding the performance of Java streams, and more. You'll also learn tips and best practices for managing the footprints of Java applications. Reducing the amount of memory needed by a Java app can provide significant performance benefits depending on your workload. Then in the next module, you'll be introduced to ways to maximize the performance of concurrent code, particularly around the areas of thread coordination and synchronization. Topics to be covered include how to size the thread pool, how to effectively use the fork join pool, and how to minimize lock contention. The final module wraps up the course with a discussion of one of the most fundamental performance optimization techniques, which is to avoid doing expensive operations. This can be achieved either by caching the result of the expensive operation so that its cost is only incurred once, or by simply using a less expensive alternative. Modules and clips in this course are independent and can be consumed a la carte. If a clip or module is not relevant to you, then you can jump around without incurring any continuity penalties. If you choose to follow along with the course examples, you'll need an IDE and a JDK installed on your machine. All the code in this course will be run on JDK 8 or later. If you're a JDK 7 user, first of all, I'm sorry. Second, please upgrade. Third, even if you're stuck on JDK 7 for some reason, this course will still come in handy for you. When features specific to Java 8, 9, 10, or 11 are taught or demonstrated, I will explicitly point that out. The source code for this course is available as exercise files on Pluralsight as well as on GitHub. The main sample application will be a web service called EnergyMart. Using the EnergyMart service, clients can compare energy prices from different suppliers against their own consumption and get a recommendation on which supplier to choose. The service has an endpoint for uploading a meter reading and an endpoint for getting back a list of all or some of the electricity readings that have been uploaded. It also has the recommendations endpoint, which calculates the cost of electricity for each supplier's plan for the past 7 days and returns a list of recommendations based on the cheapest plan. We will use this sample application to illustrate many of the performance analyses and optimizations that will be discussed in this course. For optimizations that don't fit in the sample application, we will write smaller performance testing code to show the effects of the optimizations. So let's get started with a discussion of the factors that affect application performance. One definition of computer performance is that it's the amount of work that is accomplished by a computer system. This work can be defined at varying levels of granularity. It could be requests per second, queries per second, frames per second, operations per second, etc. But in the context of this course and of this discussion, I would like to think of performance as the number of instructions that can be executed by a system within a given time period. With performance being understood to be the number of executed instructions per duration, it goes without saying that performance is highly dependent on the hardware. The better the machine, the more instructions it can execute per second. Therefore, one approach to application performance optimization is to simply run your application on better hardware. If you notice you're bottlenecked on RAM, you can simply increase the amount of RAM available or upgrade from DDR3 to DDR4 or 5, provided your operating system and processors support this. If you're bottlenecked on disk I/O, you can upgrade your HDD to an SSD, or you can upgrade your SSD to a newer generation SSD with better speeds. Upgrading processors is not as simple, as clock speeds haven't dramatically improved in the past several years, and processors must be compatible with the rest of the components on the motherboard. So the tendency is to upgrade machines to one with a higher class of CPU. But as close as hardware improvements are to a silver bullet, hardware improvements aren't always available, and before looking to make hardware changes, there are often efficiencies that can be gained by optimizing how your application code is written and how it runs. The application code we write gets interpreted or compiled into a set of instructions for the CPU to execute. And the whole idea of software optimization is to write our application code in such a way that the CPU can execute as many useful instructions as possible within a short period of time. As a result, having an understanding of the underlying hardware architecture is key to understanding and tuning application performance. The hardware components that are typically involved in software execution are the CPU, the caches, RAM or main memory, and I/O devices such as disk and network interfaces. Program instructions and data are loaded from disk or network into main memory, and then the CPU fetches and executes the instructions from main memory. Because fetching instructions from main memory is relatively slow, there are a number of caches in between the CPU and main memory. In current systems, the L1 cache is split into two different caches, both sized at 32 kilobytes, the L1 data cache and the L1 instruction cache. Reading from L1 cache takes approximately 4 CPU cycles, which equates to about 1 nanosecond, depending on your clock speed. The L2 cache is larger than L1, typically between 256 kilobytes and 2 megabytes in current systems, and has a latency of approximately 10 cycles or 4 nanoseconds. Keeping with the trend, the L3 cache is even larger, with a typical size of 3 to 8 megabytes and slower, with approximate speeds of 40 cycles or 20 nanoseconds. The other thing to note with the L3 cache is that in a multi-core system, the L3 cache is typically shared amongst all the cores. Some systems have an L4 cache, but it's not commonplace at the time of this recording. Cache misses will cause the CPU to have to fetch instructions from main memory, which could take approximately 100 nanoseconds. This is one of the reasons why smaller programs typically run faster, because the smaller the program is, the higher the likelihood of its instructions and data fitting in cache. So if you've ever needed an excuse to not write code or to delete code, I'm giving you one right now. Write less code. It'll run faster. There's a neat project at UC Berkeley with all this information and how it's changed over time. Some more interesting insights from the project is that while finding a reference in main memory takes 100 nanoseconds, reading 1 million bytes sequentially from main memory takes 5,000 nanoseconds or 5 microseconds. Contrast this to randomly accessing a location in an SSD, which takes 16,000 nanoseconds or 16 microseconds, and reading 1 million bytes sequentially from an SSD, which takes 78,000 nanoseconds or 78 microseconds. A disk seek takes 3 million nanoseconds or 3 milliseconds, and reading 1 million sequential bytes takes 1 million nanoseconds or 1 millisecond. To wrap up the topic of hardware architecture, it's important to note that when it comes to accessing data in memory, data access patterns are extremely important. Sequential data access is generally faster than random data access. There are many reasons for this, which I won't dive into, but a practical effect is that data structures and patterns that lay out data in memory sequentially, like the Java array list, are faster than non-sequential data structures, like the linked list, for example. So how do we understand and measure system performance? There are many different ways to do so, but a really common one is a framework introduced and popularized by Brandon Gregg called the Utilization, Saturation, and Errors method. Essentially what the methodology says is that to analyze the system's performance, we should examine the utilization, saturation, and errors of every significant resource that makes up the system. For our purposes, these resources are the CPU cycles, RAM capacity, disk I/O, and network I/O. Utilization is defined as the proportion of a resource that is used or the average time that the resource was busy serving work. For example, if a disk is 20% filled, then it's said to be running at 20% utilization. Or, if in a 1-second interval, a CPU spends 500 milliseconds executing instructions, then the CPU is at 50% utilization. Saturation is defined as the degree to which the resource has extra work that it can't service. This is usually observed by seeing how much work is queued up for the service. An example is the CPU run queue, which shows the number of threads that are queued up and could be run as soon as the CPU becomes available. Another example is in the case of RAM. The size of the swap space shows how much data that cannot currently fit into RAM and is set aside until RAM space is made available. The third metric is errors. Errors is simply the count of error events for a resource. For example, the number of failed memory allocation invocations or the number of dropped packets. Errors aren't always apparent, but they are important to investigate because they can degrade performance. For example, the resource may expend some effort in responding to the error. The resource may retry an operation, which increases the amount of time to receive a response. Or, the failed resource may be a part of a pool of resources, which means that the other resources in the pool now have an increased workload. Aside from hardware resources, there are some software resources that can be analyzed using the use method. Thread pools, for example, can define utilization as the number of threads currently executing a task, while saturation can be defined as the number of items in the thread pool work queue. For locks, utilization can be defined as the time the lock was held, and saturation can be defined as the number of threads queued and waiting in the lock. If a system has a limited number of threads or file descriptors, the utilization could be the number of threads or file descriptors in use, while the saturation will be the number of items waiting for a thread or descriptor to be allocated, and the errors will be the number of allocation failures. When engaging in performance analysis, or if you're tasked with diagnosing a performance problem, it's important to know and understand the performance of the underlying hardware and software resources of the system. This is where the use method comes in handy. The use method encourages the creation of checklists which list all the pertinent resources for your system. Then for each resource in the checklist, you're to examine the utilization, saturation, and errors. High utilization plus saturation, or the existence of saturation by itself, may be signs of a bottleneck, and obviously, a non-zero error count is almost always worth investigating. By employing the use method, you can quickly pinpoint the source or sources of performance degradation, which gives you a good starting point for further analyses. Now let's take a look at a few OS-specific tools for gathering some of these metrics. Whenever performance testing or diagnostics is being run, it's important to have metrics on the pertinent hardware and software resources of the system the tests are being run on. These metrics are typically provided by various operating system-specific tools. So let's take a look at some of these tools for the Linux and Windows operating systems. I'm using a Debian 9 system for this demo, but the tool should be common to most Linux distros and versions. The VMstat tool is a versatile tool that goes beyond reporting on virtual memory statistics, but also the number of processes in the run queue, swap memory usage, block I/O, the number of interrupts and context switches per second, and processor usage. Therefore, it's a great way to get an overview of your system performance and view a number of use metrics in one screen. In the command I ran here, I asked VMstat to collect and report the statistics every second for 10 repetitions. Over here we can see the CPU utilization. CPU utilization is broken into how much time the CPU spends executing user code, also known as user time, how much time it spends executing kernel code, aka system time, how much time the CPU is idle, and how much time it spends waiting for I/O. A running application typically uses user time, but it may also use system time if it performs an action that requires running kernel code. For example, if the application needs to perform I/O, kernel code will be executed to read the file from disk or write data to the network interfaces, etc. On my system, the total CPU utilization was 2%. That is, 2% user time, 0% system time, and 98% idle time. This means that in 1 second, the CPU spent 20 milliseconds executing code and 980 milliseconds idle. The CPU can be idle if there's nothing to do, but it can also be idle if there's a running application that's blocked while waiting on a lock or waiting on I/O. Although it may sound counterintuitive, it's actually desirable to have as high of CPU usage as possible for as short of a period of time as possible. Let's say an application is completely CPU bound and executes in 4 minutes while using 50% of the CPU time. If the application is tuned so that its CPU usage goes to 100%, then the application would complete in 2 minutes instead of 4. In essence, the more CPU time an application gets, the faster it can execute. This is the logic behind adding more CPU cores or reducing blocking calls so that applications can get to the CPU faster and execute faster. The Windows operating system displays CPU utilization and other system metrics in the Task Manager and Resource Monitor graphical user interfaces. But it also has the typeperf command line tool that allows you to print the value of system performance counters to the console window. The output of the console window can also be redirected to a file. For CPU utilization, we have the run queue. Like I mentioned earlier, the run queue shows the number of threads that are queued up and could be run as soon as the CPU becomes available. In Linux, the vmstat command shows the length of the run queue. And in Windows, the run queue is known as the processor queue and can be viewed using typeperf as well. Something important to note about the output of both OSs is that in Linux, the run queue count includes threads that are currently running as well as threads that could be run, whereas in Windows, the processor queue count includes only queued non-running threads. A high run queue for a prolonged period of time is a sign of saturation and will result in performance degradation. If this situation arises, then the application needs to be optimized or more CPU time needs to be made available by moving work to other machines, upgrading the machine, etc. Memory capacity in Linux is one of the columns in the vmstat output, as you may have noticed earlier, and Windows has the equivalent typeperf command. A more interesting indicator of memory capacity issues, however, are the saturation metrics. In Linux, when the OS runs out or gets low on RAM, it'll move some memory pages to a special location on disk called the swap space in order to make room for pages that are higher in demand. This process is called swapping and is an indicator of memory capacity saturation and possible performance degradation. Now we should note that even if there is sufficient RAM, the Linux kernel may choose to move memory pages that are hardly ever used to swap space. So when looking at swap activity, we should pair those numbers with memory usage numbers as well. Windows uses the swap file differently. In Windows, the swap file is called the page file, and instead of acting essentially as a spillover space for pages that can't fit in RAM, the page file contains all the memory pages currently needed or committed to. And then RAM just contains the active working set of pages. This means that RAM essentially functions as a cache of the page file. And since every page in RAM is already in the page file, it can quickly drop pages out of RAM when it needs to use the space for something else. If a reference to a page in RAM cannot be resolved, this results in a page fault, and the page must then be fetched from disk into RAM. Therefore, one of the key metrics for memory capacity saturation in Windows is the pages input per second. This is the rate at which pages are read from disk to resolve page faults. A high value of this metric is an indication of performance degradation. Disk I/O and saturation can be monitored on Linux using the IOstat tool. On my Debian system, to get the IOstat tool, I had to run apt-get install systat. Once installed, I can run the IOstat command and view usage statistics. IOstat also has these await statistics that show the average time for read requests issued to the device to be served and the average time for write requests to be served. This time includes both how long the request spent in queue and how long it took to service the request. Therefore, it's a good indication of saturation. A high value here could be an indicator of an I/O bottleneck and performance issues. For Windows, there's the disk read bytes per second and disk write bytes per second, which show the utilization. There's also the average disk read queue length and the average disk write queue length, which show the saturation. I won't get into I/O network monitoring in this video, other than to mention that there are many tools available on Linux and Windows for network monitoring, like netstat, nixstat, typeperf, SAR, and several GUI tools. While being able to observe these metrics in real time is great, if you're doing the analysis at a later time, or if you want to be able to analyze metrics over a longer period of time, then you would need the ability to collect the metrics, store them in some data store, and analyze them using a graphing or visualization tool. There are many tools that enable this workflow, which we won't dive into in this course, with the exception of JConsole, which we'll see in a demo later in this module. But first, let's talk about application performance. Because performance is a key usability and quality metric, it's important to be able to measure and quantify the performance of your application. Phrases like make it fast or improve its scalability are vague and subjective and don't make very good performance targets. As a result, the industry has come up with widely accepted terms for quantifying performance: latency, elapsed time, and throughput. Latency, or response time, is the amount of time required to complete a unit of work. Since it's a unit of time, it's typically reported in milliseconds or seconds. In a client-server environment, latency is typically understood to be the amount of time that elapses between sending the request from a client and receiving the response. Note then that the transmission time to the server, queuing time on the server, the actual execution time, and transmission time back to the client are included in the latency measurement. This may be desirable, as the goal may be to measure latency from the perspective of the client. You may, however, want to measure latency independent of the transmission time. In this case, the best approach is to instrument the server code so that it captures the start time on the receipt of the request and the end time on the return of the response, and then calculate latency that way. Elapsed time is similar to latency, but instead of measuring the time taken for each individual operation, elapsed time measures the time taken for a batch of operations to complete. This comes in handy in cases where applications typically perform actions in batches. An example would be the amount of time it takes for an application to write 1,000 records to a database, or the amount of time needed to calculate the standard deviation of 8,760 hourly energy meter readings. The other use case where elapsed time is useful is when the operation being measured is so small or so quick that the overhead needed to measure the latency for each individual operation is disproportionate to the time needed to execute the operation itself. This is certainly the case for microbenchmarking. For instance, instead of measuring the nanosecond or millisecond duration for a single string.to-lowercase method call, we would measure the elapsed time for a loop in which we performed 1,000 or 10,000 string.to-lowercase operations and then divide that number by 1,000 or 10,000. I should caution you though, writing accurate microbenchmarking code by hand is really hard. If you want to write proper microbenchmarking code, you should use a library like the Java Microbenchmarking Harness. Throughput is the amount of work that an application can accomplish per unit of time. The unit of time is typically seconds, so you would commonly see throughput measurements such as requests per second, operations per second, reads or writes per second, or transactions per second. Throughput and latency are related. The higher the latency of an application, the higher its throughput is. To put it another way, if you can do things faster, you can do more of it. One other thing to note about throughput is that your application is limited to the throughput of its lowest throughput subcomponent. To make this concrete, take a look at this example of a simplified online shop that's broken into microservices: front-end, catalog, order fulfillment. Because the lowest throughput subcomponent is the catalog at 500 requests per second, the effective throughput of the application is 500 requests per second. It also stands to reason that in this system, the catalog system presents a bottleneck which increases the latency of the entire system. Because if the catalog service is at capacity, then requests from the front end start to get queued, which increases their latency and the average or P99 latency of the whole system. So as you can see, latency and throughput are related and affect one another differently in different instances. When we talk about measuring application performance, there are two contexts in which we do this: during production monitoring and during performance testing. Production monitoring is an operations activity. It involves instrumenting your application, collecting and aggregating the metric data, storing it somewhere, and then potentially doing some analysis, visualizations, or alerting on it. This is different from performance testing. Performance testing is a development activity. In performance testing, you define the application, component, or method under test, then generate some load against the application and measure the results. Usually, you're trying to find the upper bound of performance, either throughput or latency. Performance testing is also usually an iterative process. A test is run, the results are analyzed, some bottlenecks are identified, code or configuration changes are made, and their test is repeated to verify the effects of the change and to identify further tuning opportunities. Both performance testing and production monitoring are useful and needed. Performance testing helps you anticipate and solve performance problems, while production monitoring gives you aggregated information about your user's actual experience with your app or system. As I mentioned earlier, with performance testing, we generate and drive load towards the system. Care should be taken that the input data should be representative of how the application or code will actually be used. While random data is easier to generate, user behavior isn't random and follows certain patterns. Also, when doing performance testing, you typically need a warm-up period. The warm-up period, sometimes called a ramp-up period, is a period of time when the test is running, but the recording of the response times or throughput has not yet started. The warm-up period is needed to allow the JVM complete its class loading and to allow any runtime optimizations, cache warming, or code compilation to complete. Returning to production monitoring, there are several tools that can be used for the different phases in the production monitoring pipeline. For example, in the instrumentation, collection, and aggregation phase, we have metrics libraries like Dropwizard Metrics, Micrometer Metrics, Netflix's Spectator, and Google's Open Census and Prometheus client library. In the storage phase, we have options like InfluxDB, Elasticsearch, Graphite, OpenTSDB, Prometheus Time Series Database, and many managed commercial solutions like Datadog, Dynatrace, etc. And in the analysis, visualization, and alerting phase, we have Grafana, Kibana, JMX tools, Prometheus dashboards, and more. In this course, we won't look into the storage and analysis steps. Instead, we're going to take a look at instrumenting your code with the metrics library and viewing the metrics locally with JMX. Because I'm working with Spring Boot 2, I'll use the Micrometer Metrics library for this demo. I'll start by adding the Micrometer library as a dependency, as well as the Spring Aspects library. There's plenty of documentation on the different meters available in Micrometer at micrometer.io. But for this example, I want to know the latency of my controller methods, which means I need to create a timer for each method. I would also like to have a count of errors, which would require a counter. To create these meter objects, I need a registry. So I'm going to create a configuration class and create a meter registry bean. A meter registry is a centralized registry with a set configuration for a set of timers, counters, gauges, etc. Here I'm creating a JMX registry that will report its metrics every 10 seconds. I'm also adding a timed aspect bean for the @timed annotation. This gives me two methods of adding a timer. I can either add the @timed annotation to the bean method, or I can manually create one using one of the factory methods of the meter registry. To illustrate this, for the meter readings controller, I'll simply add the @timed method to the beans. This will create a timer with a default name that measures the execution duration of these methods. For the price plan comparator controller, I'll inject the meter registry and use it to construct a timer for the response time and a counter for the number of errors. Then, I can capture the start time and record the difference between the start time and end time in a finally block. I'll also increment the counter in the not found response block. I can now run the application. It takes about half a minute to start up because it's generating all the test data. But once the application started, I can open up a browser window and fire up a few requests. In the application, I've generated 100,000 accounts, each with 200 electricity readings. So if I test with an account number under 100,000, I'll get back a result. And if I test with a number over, I'll get a not found response. The Plan Recommendation API figures out how much each plan would cost for an account holder and recommends the plans to the account holder in order of cost from the cheapest to the most expensive. I'm firing up a few requests for existing account holders as well as some requests for non-existing account holders. I can then launch JConsole, select my application from the list, navigate to the MBeans tab, and open the metrics folder. From here, I can check out the values of the timers and counter. Here I can see the average response time for the recommend price plans timer, as well as the P75 and P99 response times. We have the same metrics available for the read readings method, and we can also see that the not found counter has been incremented. When production monitoring reveals performance problems, one of the typical first steps is to manually instrument suspected methods. This is sometimes done by adding a log statement with a timestamp and other information at the start of the method and at the end of the method. It can also be done using a timer from a metrics library. And although this can be an effective way of debugging performance problems, it requires a lot of manual intervention. Every suspected block of code must be instrumented by hand, and there's still other information that you might miss. A better alternative to manual instrumentation is to enable profiling and use a low overhead production profiler. We'll take a deeper look at profiling in Module 3, but first let's talk about performance testing tools. The first tool every Java performance tester should have in their arsenal is Java Mission Control, JMC. Java Mission Control is a tool for collecting low-level and detailed runtime information from a JVM. It integrates information available in all the older standalone apps like JStat, JInfo, JMap, JStack, and JConsole. Of course, there are a few pieces of functionality still found in the standalone apps that JMC doesn't have, but for the most part, JMC is a Swiss Army knife. In addition, JMC contains a graphical user interface for Java Flight Recorder, a profiler that we'll look at in the next module. JMC can connect to both local and remote JVM processes. To connect to a remote JVM process, you must first enable JMX monitoring. This is done at JVM startup time by passing the appropriate properties on the command line or setting them in the Java ops environment variable. In a production environment, you should have some level of security set up. JMX provides pluggable login modules for security. By default, it provides password and certificate-based login. Details on setting up security can be found in the Oracle Java documentation. If you're running Oracle JDK 7 and above, then JMC is already bundled in your Java bin directory. And if your path is set up correctly, you can simply type JMC on your command line to launch it. In OpenJDK 11 and higher, JMC may not be bundled and may require a separate download. In that case, you can go to jdk.java.net/JMC, download and install the JMC binary for your operating system, configure your path, and now you can launch by running the JMC command. When you open JMC, it'll automatically detect all running local JVMs on startup and connect to them for you. You'll see this list on the left JVM browser view. If you see a welcome screen instead, you can close it to reveal the default view. To connect to a remote process, you can either click File Connect or click the new connection icon. Here you can specify the host name and port for the machine you'd like to connect to, and if you set up password authentication, then you'll input the configured username and password here. Before we look at the features of JMC, I'd like to introduce you to another important Java tool, JCMD. JCMD is the command line equivalent of Java Mission Control. Like JMC, it integrates JMap, JStack, JStat, and JInfo into one tool. However, unlike Mission Control, it cannot connect to remote processes. Therefore, JCMD is useful if you want to monitor a JVM process on a remote server, but for some reason you're not able to enable remote JMX monitoring on that remote process. If you have SSH access to that server, you can SSH in and run JCMD to get all the information you would have gotten with Mission Control. You may also prefer JCMD if you tend to be more of a command line user than a GUI user. And if you intend to do some scripting, then JCMD is your only choice. Just typing in the JCMD command lists all the currently running JVM processes. This gives you the process ID of the process and the main class name. You can use either to specify the JVM process you want to diagnose. To use JCMD, you type the process ID or class name, then you either type in the command or a file with a list of commands to execute. To view the list of available commands, type in JCMD, the process ID, and help. This displays all the available commands supported by the target JVM. There's also the perfcounter.print command. When you run it, you can see the counters like the number of classes loaded and unloaded, the number of live threads, the GC stats, and more. Now let's take a look at some of the diagnostic information that we can get from Mission Control and JCMD. I'll right-click on the Energy Mart app and select Start JMX Console. The first tab is the Overview tab, which gives you a dashboard with a number of gauges and graphs. You can add more gauges by clicking the plus button here and selecting the gauge to add. You can also move gauges around and remove gauges that you don't need. There's also graphs below for monitoring CPU and memory performance. Like the gauges above, we can add additional metrics when supported. The processor graph shows the system CPU usage and the CPU usage of the selected JVM process, and the memory graph shows the physical memory available as well as the heap memory available and used. These metrics can be toggled on and off. There's no equivalent option in JCMD, but we have the regular performance monitoring command line tools like we talked about in the previous video clip. If we go to the System tab, we can see basic information about the JVM host, such as the class path and the VM arguments. We can also see the values of all the system properties that can be seen by the JVM. In the Diagnostic Commands tab, we can view select JVM tuning flags by selecting the vm.flags command and clicking Execute. There are hundreds of JVM tuning flags, and the command just prints a few of them. This output is identical with the output of running JCMD with a process ID and the vm.flags command on the command line. To print all possible tuning flags, add the -all option. In the output, the first column is the type of the flag, the second column is the flag name, and the third column is the value of the flag. In older versions of JCMD, this equal sign could be prepended by a column sign, and the column sign would indicate that a non-default value was set. This could be either because the value was manually set, or was set indirectly as a result of a change to another option, or was calculated by the JVM based on the runtime environment. This information has now been moved to the last column. The fourth column specifies whether the default setting of the flag is uniform across all platforms, whether the setting is platform dependent, or whether the setting is changeable at runtime. Let's find an example of a flag that's manageable, meaning it can be changed at runtime, and note its default value. To change a tuning flag at runtime, you can use the vm.setFlag command. You should only attempt to change a flag at runtime if it's marked manageable. Otherwise, although your change may be reported as successful, it won't actually be applied to the JVM. For some JVMs, for example earlier versions of Oracle JDK 8, the vm.setFlag command is not one of the available commands. In this case, you'll have to fall back to the standalone jinfo command line tool. I'll execute the jinfo command to modify the value. I can then go and verify that the value has been changed. JCMD does not have commands for viewing or editing MBeans, so you're limited to Mission Control here. With Mission Control, you can view the values of all MBeans registered to the specified JVM process. And for MBeans that are editable, like the compressed class space usage threshold, I can change the value. The Threads tab captures information on all currently running threads in the JVM. The Live Threads graph shows you how many threads are running in the system. If you have a service that spins up a lot of threads, then this graph could be interesting to you. We also have the Live Threads table. It has filtering capabilities, so if you're only interested in HTTP threads, for example, you can view just the HTTP threads. This is where explicitly setting your thread name comes in handy. For each thread, you can view the thread name, its state, and its blocked count. A thread can be runnable, which means that it's currently doing something, blocked, which means that it's encountered a lock that it's blocked on, or it can be in a waiting or timed waiting state, which means that it's waiting on another thread to perform some action that it can react to. The blocked count column gives you a count of how many times the thread has been in the blocked state. In addition to thread state information, Mission Control can show you the total CPU usage of each thread, whether it's deadlocked or not, and how much memory is allocated to each thread. I can also get most of this information from JCMD, minus the thread allocation and deadlock information. The JCMD output shows some CPU information, such as whether it's a daemon thread or not, the thread priority, and how much CPU time it spent. It then gives you the thread state and a stack trace. By the way, older versions of JCMD may not have the CPU time, and you'll have to fall back to mission control or other tools for that information. The last tab we'll look at is the memory tab. Here we can see the size of the different heap areas like Eden, Survivor, and Old Gen, as well as the size of non-heap pools like the code cache, metaspace, and compressed class space. We can then take a look at garbage collection and see how many young generation collections have occurred and how long they took in total. This information is available for the old generation collections as well. In JCMD, the GC heap info command provides the very useful heap info. Just like in previous examples, there are some JVMs that don't have this command available, and in that case you have to fall back to using the JStat command and passing in the -gcutil flag. The output of JStat is a bit cryptic without knowing what the headers mean. You can refer to the online documentation for the version of JStat that you're using for what these headers mean. For example, E is the percentage of the current Eden capacity used, and O is the percentage of the current old gen capacity used. YGC is the count of young generation collection, while FGC is the count of old generation collections. The last thing we'll look at is the heap histogram feature of mission control. The heap histogram shows the total size and instance count for each class type in the heap. Here I can see that we have over 20 million instances of big decimal, instant, and electricity reading taking up the vast majority of the heap space. These numbers alone tell me a lot about where my memory consumption is going. But if my app is experiencing out-of-memory errors, it would be beneficial for me to take two histograms, maybe a minute or two apart, and look for trends in which instances are growing and which aren't. I can do this easily in JMC by clicking the button again to update the histogram. And now I can see the delta between the values of the current and previous histogram in terms of size. I can sort by delta to see which instances are growing the most. In JCMD, I can use the command gc.classHistogram to generate the histogram. Unfortunately, JCMD won't give you the delta between two histogram runs, so you'll have to write your own script to do this, or find one online that's already been written for that explicit purpose. JCMD also allows you to initiate a full heap dump that can later be analyzed by a heap analysis tool like JHat or Eclipse Mat. We'll take a closer look at the Java heap in a later module, but first, let's talk about Apache JMeter. JMeter is a tool for load testing and analyzing the performance of web applications. It supports highly concurrent tests, allowing you to simulate heavy load on a server. Once a test is completed, JMeter will produce a detailed HTML report that allows you to easily view and analyze the service latency, throughput, and errors. To install JMeter, visit the JMeter downloads page, download the tar or zip archived binaries, and extract them to a location of your choosing. To create and execute a load test, you first need a test plan. A test plan describes a series of steps that JMeter should execute. JMeter gives you the flexibility to make a test plan as simple or as complex as you want. For example, you can have a test that logs into an application via the login page, saves the cookies, navigates to the search page, executes a search, has a delay, does some branching logic, and then navigates to another page based on the branching logic. To provide this flexibility, JMeter gives you building blocks to control every part of a test plan. Some of the components we have are thread groups, samplers, logic controllers, listeners, configuration elements, assertions, timers, preprocessors, and postprocessors. Thread groups are exactly what they sound like, a group of threads to execute your test. The number of threads in the group determines the number of concurrent calls or users. In JMeter, thread groups also allow you to control the number of times to execute the test, or the test duration, and the length of the ramp-up period. Samplers perform the actual work of making the HTTP or Java request. In addition to HTTP and Java, there are many other request types supported, like JDBC, TCP, SFTP, and more. Controllers are used to determine the sequence in which samplers are processed. Controllers provide branching, looping, random order execution, only once execution, and more. Listeners listen to the results of samplers and can then save the responses, view them, provide graphs and reports, and more. Configuration elements can be used to set up defaults and variables for later use by samplers. Examples are the HTTP Cookie Manager, HTTP Request Defaults, User-Defined Variables, and the Random Variable Configuration element. Assertions can be used to provide checks on the requests, or more commonly, the responses of samplers. For example, an assertion can be used to check that the response contains a certain text in the body, or the response is returned within a certain amount of time. Timers can be used to add pauses between the execution of requests. Timers can be constant, random within a range, or designed to achieve a certain throughput. Lastly, we have preprocessors and postprocessors that can be used to add functions that can be run before or after requests. Because test plans can be arbitrarily complex, JMeter provides a graphical user interface for building test plans. After building your test plan, you can run it in the GUI for debugging purposes. But to run a proper load test, you should do it in command line mode. For the purposes of this course, our test plan is simple. I want a thread group with a number of threads, a 10-second ramp-up time, and a set duration. I'm using a JMeter function for setting the number of threads and the test duration. The first argument is the name of the property, and the second argument is the default value to use if the property is not set. Then I'll add an HTTP sampler to make requests to the running EnergyMart service with an account ID chosen at random using the random function. I'll also add a timer to insert a pause between requests. The pause time should be 300 milliseconds plus a random jitter time that's under 100 milliseconds. That's all I need for my test plan. I can save and exit here, but in order to debug this test, I'll add a View Results Tree listener, save the plan, and run it. I can now see that it works. Random accounts are requested and the results come back. So I'll go ahead and delete this unnecessary listener, save the test plan again, and exit. I'm choosing to run JMeter locally on the same machine that my service is running. This is not ideal, as my test runner and my service will be contending for the same resources. JMeter has a nifty feature where you can run JMeter in server mode on a remote server or servers, and then control the servers from your client machine. I won't demonstrate that in this video, but there's plenty of documentation on how to do this on the JMeter website. Load test should be run from the command line. Here's a sample command for running a load test. -n means that it should be run in command line mode. Then I'm specifying the load test file and a file name for outputting the results. I'm also passing in user-defined variables for the number of concurrent threads and the duration of which to run the test. When I hit enter, the load test starts and JMeter intermittently prints out some summary statistics to let me know how it's doing. When the test completes, the results are stored in a JTL file. To generate an HTML report from the JTL file, I'll run the JMeter command with the -g flag, specifying the target JTL file, and the -o flag, specifying a target output directory. This will create an HTML report in the named folder that can be viewed in the browser. The index page of the report is a dashboard where you can see the average response time statistics for your requests broken down in percentiles. Here, I can see my average response time, the 90th percentile response time, and the 99th percentile response time. I can also see the throughput and network traffic. In addition to these stats, the dashboard also contains information about errors. In the throughputs graph section, I can see how the throughput changed over time, starting at 180 hits per second, and then going to 328 hits per second, before dropping to about 100. I can also see what the response time is as the number of requests per second increases. Here I can see that at 5,000 requests per second, my response time jumps. The response time graphs shows the distribution of response times either in 500 millisecond buckets or 100 millisecond buckets. These are just a few of the features of JMeter. There's a lot more functionality in the controllers, listeners, and other elements that are well documented on the website. In this module, we defined performance as the amount of work that is accomplished by a computer system, and we talked about how hardware affects performance. We then looked at how to measure system performance with the use methodology and various operating system tools for getting these metrics. We discussed application performance metrics and how to capture them using metrics libraries. Lastly, we put together a performance testing tool suite for getting detailed runtime information from a JVM and for generating load on a service and measuring the results. In the next module, we're going to take a look at how we can use Java profilers to analyze and troubleshoot application performance issues.